Welcome to video 7. We're talking about acid and base titrations. We can use neutralization reactions, we just talked about those, to determine the concentrations of unknown acids or bases. That's kind of the goal of using neutralizations, is we take something unknown and find its concentration. The process of adding a measured amount of a solution of known concentration to a solution of unknown is called a titration. It's basically where we keep track. We have a solution we know information about. We keep track of how much we're adding, but we're adding that to something we don't know information about. And our goal is basically to figure out information about the unknown. The steps in a typical acid-base titration are, first, a measured volume of an acid solution of unknown concentration is added to a flask. So we can at least measure the volume. We may not know the concentration, but we put that in a flask. Step 2. Several drops of an indicator are added to the solution, and we gently swirl it. So put a couple of drops of indicator. Common ones are phenolphthalein. Sometimes you'll see methyl orange or even universal indicator if you really wanted to overkill it. Phenolphthalein, those are most common. 3. Measured volumes of a base of our known concentration are mixed into the acid just until the indicator changes color. It's actually what we're going to end up calling our endpoint when the indicator officially changes to the color we're looking for. By the way, the solution of known concentration we call our standard solution. So that's the one that we're slowly adding into it. And the equivalent point is the point at which neutralization occurs. Then this is the point at which the number of moles of our hydrogen ions are equal to the number of moles of hydroxide ions. Most of our calculations are going to come from this concept. Fortunately, this brings us back to stoichiometry, which I know not everyone likes, but we're able to basically do these calculations with equal number of moles. All right, how many milliliters of 0.45 molar hydrochloric acid will neutralize 25.0 milliliters of 1 molar potassium hydroxide? As always, our first step is to write an equation. So, take a few minutes to actually try and draw that equation. Keep in mind, here's our two reactants. Come back in a bit. Strong acid plus a strong base produces salt and water. Now we got to make sure we got this equation balanced. Done. Okay, it's balanced. Doesn't always happen like that, but in this case it does. So, ultimately what we've got is the following information. Basically, we have our molarity for both, but we're looking for how many milliliters will actually equal this. Now, ultimately, the long process that I originally taught you guys is convert this amount to moles, move over to moles, and then actually form out molarity. And that's an all-functional process. It's great. However, you get to the point where that just kind of gets tedious. You're doing a lot of calculations and kind of, to be honest, wasting a decent bit of time. So here's a common equation that's going to help you a bit. And here it is. So we have that M1 V1 over C1 equals M2 V2 over C2. M1 and V1 stand for the molarity and volume of the first compound, M2 V2 of the second. C1 and C2 represent the coefficients of those compounds, which in this case are both 1, so it won't really change anything. But in our second example, it actually will a bit, so it helps to factor that in. All right, so when we plug those values in, here's what we get. We get 0.45 times x. I put that to solve for our molarities. Over 1, that's again our coefficient, that's why it's red. You don't really need to put the 1, but it's a good habit. 1 times 25 over 1. All right, so if we actually divide by 1, simplify, solve for x, our final actual volume that required is 55.6 milliliters. So, again, you actually could just convert these to moles, move them over, convert back down to liters. That's fine. This is just another way to do it, and often comes a little bit faster. It relies on the fact that this will occur at equivalence point, which is when the moles of our acid are equal to the moles of our base, at least according to stoichiometric ratios. Cool. Let's do another example. Okay, so our very first step is actually to find our balanced equation. Hopefully you're able to find it, but if not, here you go. Now that we have our balanced equation, I'm going to actually write down the information that our problem gave us. So, now we actually have a list of the information given. We can now use the equation I talked about last time. M1, V1, C1, which this time is still 1. M2, V2, C2, this time is a 3. Plugging in our values, we get, alright, here we have our final values. Lastly, working out for x, or solving for x, we get that our concentration would be 0.13 molar. Alright, equation, write what you're given, plug it in, make sure you actually got it set up properly, find your final answer. That's how you actually perform the calculation for titrations. Thanks for watching.